Welcome to Physics for Real. Today we're going to look at an international baccalaureate question from the November 2019 paper. So this question is all about capacitors. So what you can see here is we've got two capacitors connected in parallel, and one of them is charged and one of them is uncharged. So this capacitor is charged and has a charge of 48 microcoulombs on it. This capacitor has a charge of 0. And we know the capacitance of X is that 18 microfarads. So the first thing we're asked to do is work out the energy stored in this capacitor. So the way we can do that is E equals half CV squared, but we also know that Q equals CV. So if we rearrange that, we're going to get V equals Q over C, and then V squared equals Q squared over C squared, which we can then substitute into this equation to get half CQ squared over C squared, and then they cancel out. So we can use this equation now. E equals half Q squared over C, and we can put the numbers in. So half times 48 times 10 to the minus 6 squared divided by 18 times 10 to the minus 6. And that's going to give us an answer of 6.4 times 10 to the minus 5 joules. All right. Now, if we move on to the next part then, so we'll clear the page there. Part B, we're told that Y has a capacitance of 12 microfarads and the switch is closed. So what's going to happen now is when the switch is closed, if this is positive and this is negative, so originally we've got some voltage across here, okay, and this has a voltage of 0. And we know that the charge is obviously, there's a charge on X of 48 microcoulombs, okay? And what's going to happen then is when we close the switch, the negative electrons are going to flow off the bottom plate of X and they're going to flow onto the bottom plate of Y. So this is going to start to gain a negative charge, and electrons are going to be attracted off the top plate of Y onto the top plate of X. So that's going to gain a positive charge. So essentially the charge on X is going to go up, but this charge on Y, let's say that again. The charge on Y is going to go up, but the charge on X is going to go down, okay? And that's going to continue happening. And as that happens, the voltage on Y will go up and the voltage across X will go down. And that will continue happening until the voltage of both capacitors is equal, okay? So because we know that Vx is going to equal Vy, we can say that Qx over Cx, because obviously V equals Q over C, is going to be equal to Qy over Cy. Okay, so that's our starting point. Now, the important thing to understand here is the charge on X, this charge here is going to decrease, and the charge on Y is going to increase. But however much that goes down is the same that goes up. So however much the charge on Y goes up, the charge on X will go down. But the total charge on the two capacitors together is going to remain the same. So we know that Qx plus Qy is going to equal 48 microcoulombs, okay? So these are the equations, these are the things that we need now in order to answer the question. So we're going to start to put numbers into the question. So I'm going to just answer this here. So obviously this is not this question. This is I'm doing question B here, okay? But I'm going to answer it here. So Qx over Cx equals Qy over Cy. Okay, that's Y there. Now we know the capacitance of both capacitors. So we know this and this, but we don't know this and we don't know this. So we can't solve the equation because there are two unknowns. However, we can rearrange this equation and then substitute it into this equation to help us solve it. So what we can say here is we know that Qx is going to equal 48 microcoulombs minus Qy, and then we can substitute that into there for that. So we know that 48 times 10 to the minus 6 minus Qy over 18 times 10 to the minus 6 is equal to Qy over 12 times 10 to the minus 6. So we just put the numbers into the equation and that's what we get. Right, so if we rearrange this then, we can take this over here onto this side, okay? So we can basically multiply both sides by 18 microcoulombs, or sorry, 18 microfarads. Multiply both sides by 18 microfarads, and that's going to get rid of that. Okay, so let's do that. So what we've got now is we've now got 48 times 10 to the minus 6, minus Qy is going to be equal to, let's get rid of that. Let's get rid of all that. Get out of there. Okay, so that's going to be equal to Qy multiplied by 18 times 10 to the minus 6, over 12 times 10 to the minus 6. Okay, so we've got to rearrange that again. So the way we're going to do that, we know that this equals 1.5. So basically we can simplify the whole thing now, because we can rub that out and we can write 1.5, okay? And then what we can do is we can take this over to this side. Okay, so when we do that, we're going to get plus Qy on this side, and that gets rid of that. Okay. All right, so now we just need to simplify this. So 1.5 Qy plus Qy gives you 2.5 Qy. Okay, and therefore I'll come down the bottom and do this. Qy is going to equal 48 times 10 to the minus 6 divided by 2.5, okay, and that will give you an answer of 19.2 times 10 to the minus 6, but we should quote it only to two significant figures because all of the data that we used was to two significant figures. So there's our answer. Now all that remains then is to work out what Qx is. So if I rub some of this out, we can do it up here. All right, so let's get rid of all of that. So we can just work that out now by using this equation that Qx equals 48 times 10 to the minus 6. Okay, so we know that Qx is that, 48 microcoulombs, take away Qy. So now that we know Qy, we can take away 19 times 10 to the minus 6 from that. And that's going to give us an answer then of 29 times 10 to the minus 6 coulombs. Okay, so we've got Qx and Qy. All right, so the last thing to do then, last couple of things to do are these. It now says calculate the final total energy stored in Y. The final total energy stored in joules on both capacitors. So we've got to work out the final total energy stored in capacitor X and Y together. So the way that we're going to do that is as follows. So we know we've got the equation E equals half Q x squared over cx plus qy squared over cy. So we're just going to work out the energy stored by adding up the energies on both capacitors. So the way we're going to do this then, half times 29 times 10 to the minus 6. I'm going to square that, divide that by 18 times 10 to the minus 6, plus half times 19 times 10 to the minus 6 squared, because that's the charge on capacitor Y, divided by 12 times 10 to the minus 6, because that's its capacitance. And when you work that out, you're going to get a total of 3.8 times 10 to the minus 5 joules, okay? So that is the answer for that one. All right, so the final thing then is this, it asks us then why your answers to A and B part 2 are different. So remember, A was the charge stored on capacitor X before it was discharged to before we closed the switch, and then B part 2 was the energy stored on both capacitors. So the first thing to say there is the energy stored in this first part here was 6.4 times 10 to the minus 5 joules. Okay, that's before capacitor X was discharged to capacitor Y. And then the final energy on both, so that's part A, the final energy on both was 3.8 times 10 to the minus 5 joules. So why is this less than this? And the reason is that, let's get rid of all that. So I think that was negative and that was positive. So the reason is that as the charge flows onto capacitor Y, okay, what's going to happen is a current is going to flow through the circuit, okay, and as it does that, the wires are going to get hotter, okay. So as the current flows, the wires get hotter, and some of this energy is used to overcome the resistive forces essentially, and is produced and basically turns into heat in the resistor and heat in the wires, and that's why this is less. Okay, so we can do that then just to finish off. We can write that down and then we will leave it there. So the reason is a current flows as charge moves from capacitor X to capacitor Y, and then energy is converted to heat by resistive forces. Okay, so there we go. Thanks for watching.